Hey everyone, and welcome to today's Explainer. I am absolutely thrilled you're here because we're looking at one of the most fascinating paradoxes in the history of science. We're going to dive into the work of John Dalton. He was an early 19th century English chemist who formulated a theory so groundbreaking it literally revolutionized how we understand the physical world. But here is the central mystery we're going to unravel today. Dalton's atomic theory, which he published back in 1808, was incredibly brilliant. And yet, as time went on, several of its core rules were proven absolutely, undeniably wrong.
So think about this for a second. How did a theory with so many fundamental errors become the unbreakable foundation of modern chemistry? It sounds totally counterintuitive, right? Usually, when a scientific theory is proven wrong, it just gets tossed out, but not Dalton's. Today, we're taking a close look at the very nature of scientific discovery to understand how being partially wrong is sometimes the exact stepping stone we need to become completely right.
Okay, let's dive into this. Here is our roadmap. First, we'll trace the shift from philosophy to hard science. Then, we'll break down Dalton's atomic theory, dig into the law of multiple proportions, smash the indivisible atom, and finally explore the isotope exception.
Part 1. Philosophy to hard science. From guesswork to quantitative data.
You know, to truly appreciate what Dalton did, we kind of have to understand the landscape of chemistry before he even came along. The idea of the atom wasn't actually a new concept, but the method of proving it, that definitely was. Thousands of years ago, the ancient Greek philosopher Democritus hypothesized that everything was made of these indivisible particles. But let's be real, he was essentially playing a philosophical guessing game. He had absolutely no numerical data. It wasn't science. Now, fast forward to Dalton in the early 1800s. As the modern concept of elements like iron and oxygen was finally taking shape, Dalton had a crucial advantage. He actually used the scientific method. He backed up his ideas with solid, verifiable, quantitative elemental analysis. He actually measured things.
And Dalton didn't work in a vacuum. He built his theory on the shoulders of giants like Antoine Lavoisier. Historically, people thought that when you burned a piece of wood, the mass just disappeared, right? Because you were just left with this tiny little pile of ashes. But Lavoisier's law of conservation of mass proved that if you actually capture the invisible gases, the carbon dioxide and the water vapor, the mass of the burning wood and oxygen perfectly equals the resulting ashes and gases. Mass isn't lost, it just changes form. So Dalton took this foundational rule and asked himself a pretty huge question. What must matter be made of for this to actually be true?
Part 2. Dalton's atomic theory, the 5 pillars of 1808.
Dalton managed to synthesize the chemical laws observed by his predecessors into one unified, elegant theory of matter. I want to share a quote directly from his groundbreaking 1808 publication, A New System of Chemical Philosophy. He wrote, "Chemical analysis and synthesis go no farther than to the separation of particles one from another, and to their reunion. No new creation or destruction of matter is within the reach of chemical agency." That right there establishes Dalton's absolute conviction in the permanent, indestructible nature of matter. You can't create a new particle, and you definitely can't destroy one. You can only shuffle them around. It's like a giant puzzle.
So here they are, Dalton's 5 core postulates. First, matter is made of extremely small, indivisible atoms. Second, all atoms of the same element are absolutely identical in mass and properties. Third, atoms of different elements vary in size, mass, and behavior. So a gold atom is just totally different from a silver atom. Fourth, compounds are formed when atoms of different elements combine in simple numerical ratios. You can't have half an atom. And fifth, chemical reactions only rearrange atoms. None are ever created or destroyed. Back in the early 19th century, these were laid down as undisputed scientific facts.
Which brings us to part 3, the law of multiple proportions, the math behind the matter.
And this brilliantly illustrates where Dalton's genius truly shines. He didn't just theorize, he looked at the hard numbers. Specifically, he studied different oxides of tin. He found a gray powder, which he called a protooxide, and a white powder, a deutoxide. When he measured them out, he found that for every 100 grams of tin in the gray powder, there were exactly 13.5 grams of oxygen. But in the white powder, for every 100 grams of tin, there were 27.0 grams of oxygen. Just look at those oxygen masses for a second. 13.5 and 27. That is a perfect, literal 1-to-2 ratio. This tangible math proved his 4th postulate. Elements don't just mix randomly, they combine in multiples of a basic quantity, in small whole numbers. This was a massive triumph for atomic theory.
Moving right along to Part 4, breaking the indivisible atom, smashing Dalton's first rule.
Okay, so for nearly a century, Dalton's rules were absolute gospel. But then, technology caught up, and we realized something absolutely staggering. Yes, atoms exist, but they aren't indivisible. The late 19th and early 20th centuries were pretty brutal for Dalton's first rule. Over just a few short decades, scientists systematically smashed his idea of a solid, unbreakable atomic sphere. In 1897, J.J. Thomson found the electron. In 1909, Ernest Rutherford found the nucleus, and in 1933, James Chadwick completed the puzzle by discovering the neutron. The indivisible atom had officially been divided.
Let's talk about how Thomson actually pulled this off. He used a cathode ray tube. Basically, it's a vacuum tube where electricity passes from a negative to a positive terminal, creating this glowing green ray. Thomson noticed that if he brought a magnet near the tube, the ray physically bent away from the negative magnetic pole and toward the positive one. Since only negatively charged material behaves this way, he proved these weren't just weird rays of light, they were tiny, negatively charged particles smaller than the atom itself. He had just discovered the electron.
Then Ernest Rutherford took it a massive step further. After the electron was found, scientists kind of assumed the atom was like a plum pudding, this positive sphere with negative electrons just floating around inside it like little plums. Rutherford tested this by firing a beam of alpha particles at a microscopic, incredibly thin piece of gold foil. If that plum pudding model was right, the particles should have just passed straight through. But while most did go through, some violently bounced right back. Rutherford was completely shocked. This proved that atoms are mostly empty space, but right at their very center is a dense, incredibly small, positively charged core, the nucleus.
Now for Part 5, the isotope exception, breaking Dalton's second rule.
So, we've established that Dalton was totally wrong about atoms being indivisible. But unfortunately for his 1808 theory, he was also wrong about his second rule, that atoms of the same element are perfectly identical in mass. The culprit here is the isotope. An isotope is simply an atom of the same elements that has the same number of protons, which, remember, is what gives it its chemical identity, but a different number of neutrons. And because neutrons carry actual physical weight, this results in the atoms having completely different masses.
Let's use chlorine as a concrete example. Out in nature, chlorine comes in two stable isotopes, chlorine-35 and chlorine-37. They behave exactly the same way chemically. They both have 17 protons. But chlorine-37 has 2 extra neutrons, which simply makes it heavier. So Dalton's absolute rule that every single atom of the same element has the exact same mass, it completely fails in the real world.
And just to add one more little wrinkle, here's another anomaly Dalton couldn't quite explain: allotropes. Think about charcoal, graphite, and diamond. They are literally all made of carbon atoms, the exact same building blocks. But because of how those atoms are structurally arranged, they have vastly different physical properties. Once again, nature just proved to be far more complex than Dalton's overly rigid initial rules.
So, this brings us to a really crucial point. If Dalton was wrong about atoms being indivisible, and he was wrong about atoms of the same element having identical mass, why on earth do we still use his theory? Why is he featured in literally every chemistry textbook in the world today?
Well, the answer lies in his lasting legacy. Dalton's theory was a flawed masterpiece. It correctly provided the mechanism for Lavoisier's law of conservation of mass. It perfectly explained Proust's law of constant composition. Dalton himself proved the law of multiple proportions. By giving us this framework of atoms combining in fixed numerical ratios, Dalton gave future scientists the exact macro-level mathematical foundation they desperately needed to eventually discover the micro-level truth. Without Dalton organizing the elemental world into manageable rules, the modern periodic table simply would not exist.
Which brings us to our final takeaway for today. Science is an evolving draft. John Dalton wasn't a failure just because some of his postulates were later corrected. He was a pioneer. His theory was robust enough to hold up for a solid century and flexible enough that when new tools like the cathode ray tube came along, we could refine his theory rather than just throwing the whole thing away. Being partially wrong really is the very first step to becoming completely right. So as we continue to smash particles and peer even deeper into the quantum realm, it leaves us with one thrilling question to ponder. What unbreakable scientific law are we going to rewrite next? Thank you so much for joining me for this explainer. Keep asking those big questions, and I'll catch you next time.